Hello everyone, welcome to Computer Science 401, lecture number 19, I think, already. Anyway, so today we'll be talking about statically based allocation, heap-based, and stack-based. Okay, so there are basically three ways how programming languages allocate some data. And those are the three ways. We briefly talked about, I think, static allocation last time, but today let's go a bit deeper into them. Let's compare them and how they're used, which one is used, and which one is actually available to you and which one is not available to you. So if we take a look at here, if let's say that is our RAM, okay, that's the high addresses of the RAM, there's the low addresses of the RAM. So let's say again you have I don't know like 8 gigs of RAM, so that would be like the 000 addresses over here and very high like FF addresses over here. So usually data which is statically allocated, it's usually located somewhere in the top. Okay, so that's the data which nobody touches. So what, like in general, if we don't talk about any specific programming language, if we don't talk about Java in particular or like C, so like on average how it usually functions, is that all the global variables, all the static variables, all the data, all the variables which is possible to predict how much memory it will take, it's usually located on the statically. It's usually located over here. Okay, so for example, if you know that array is going to take, I don't know, like 500 bytes, in this case usually it's located over here, somewhere in this region, then yeah. Okay, so again, all the global, all the static, the garbage collection, all the stuff which is needed for the compiler, for the program itself. Because, for example, if you have a main method in Java, then main method is called some other method, then something needs to be actually, like Java virtual machine needs to be executing, right? So like how do you go from one method to another method? And that's usually, so the information about how it's done is usually kept here. So not specific execution, but information about how that should be done. So basically, again, the kind of, I don't know, the eclipse. So the program which runs your code. So you're the one who's writing the code, and the program which runs the code is located somewhere over here. So it's located statically. Okay. Then over here next we have stack, and over here we have heap. Okay, and that brings an important part. So that's the stack, smiley face, and the gloomy face is the heap. Okay. What happens is that stack grows downwards, so it goes from over here. There is some location, and you can actually look it up in the data sheets for all of the chips. Okay, but anyway, starting from some location, stack grows downwards. Okay, so it grows that way, while heap grows this way. And statically allocated data doesn't grow anywhere usually. Anyway, so that's the stack, that's the heap. They grow kind of like towards each other, and as you know, that stack overflow, when does that happen? That happens when they meet. Okay, so when the stack grows so big, such that it actually meets the heap somewhere. In this case, you have the stack overflow. Okay. So one more time, statically allocated data is for those everything global, everything shared, static data, static methods, Java virtual machine, usual like some different routines, all that stuff. So that's located over here. In the stack, we usually have everything which is related to recursion. For example, in Fortran back in the day, recursion was not supported. That's why if a method was calling another method, then in this case, like the data between the methods, the parameters which were passed between one method and another method, they were located in the statically allocated data, like in this region. Okay. Nowadays, since we have recursion, it's possible to have like it's possible to call for a function to call itself 1 million times. Of course, again, like if you set aside some fixed amount of data, that's not very efficient because you have no idea, again, what was like 1 million of calls, 2 millions of calls. That's all possible, right? So basically, in this case, you need to be flexible. You need to grow the region which you reserved for that particular operation as you go in. So you don't really know exactly how much memory you will need. And in that particular case, again, the stack is useful. So you can grow it downwards. Yeah, and yeah, so another question actually a lot of people ask at the interview is this: who has the control over it? Who has the control over those memory locations? Okay, now When we're talking about statically allocated memory, you have the user has no control. The program, the operating system is usually controlling that. Now, when we're talking about the stack-based allocation, user has no control over the data either. It's usually the calling subroutines, the compiler, the Java virtual machine, not the operating system usually. Okay, Java virtual machine, it's some routines like in your code in Eclipse. They're controlling the stack. Okay, but not you. Very important, definitely. So not you, not the programmer. And heap. So heap is the data which is also dynamic, so you can basically say, hey, give me like 2 more like megabytes, 2 more gigabytes of data, like I need that. Okay, so the user is requesting the operating system basically, hey, please can you give me some like this amount of data. So he specifically says that, hey, I need that amount of data, and the user and the system goes, okay, cool, so like let me check. It basically goes ahead and checks like if it has like 2 gigabytes of consecutive data. So usually it basically checks like if it can grow, right, if it can move that border up a little bit, like for 2 gigs, and then it returns you as a programmer reference point, so the address of those 2 gigs which are given to you. And that's kind of the agreement between you and operating system. The operating system, Java virtual machine, the compiler, Eclipse, they basically say, okay, look, so that data is for you. We are not going to touch it at all. If you make any mistakes, those are your mistakes. Just do whatever you want with this. We're not going to like touch it. Okay. So what does that mean? That's basically kind of good and bad. It's good because you have full control over that, right? You can do just whatever you want. The compile optimization, anything, nothing will be touching that. So like you kind of like the guru, you're the master there. However, that also means that it's prone to mistakes. Like the stack and the like statically allocated data. So all the routines which manage that memory, they have no errors. They're prone to be so definitely like huge amount of people tested them. They definitely work correctly. However, if I ask the system to give me 2 gigs of data, it gives me 2 gigs of data from the heap. Okay, so what happens is that, okay, I ask that, they give me the reference point, then they promise not to touch it, and then let's say at the end of the program, at the end of the code, I forgot to return it back to the system. Okay, so I have 8 gigs of my RAM, I requested 2, so now I own 2 gigs. I forgot to give it back to the system. Now, system is always going to think that it's still being used and it's still needed. Okay, because I didn't give it back. So it's now, so basically, although I already quit the program, right? So that's why that 2 gigs of data, they become dead. Nobody can use it. There is no advantage usage of it. Operating system is still thinking that you're smart enough and you're using that and it's needed. It's not going to touch it either. Yeah, hope it makes sense. In general, that's the idea. So when we're talking about the heap, the interview, there are a lot of questions about who's controlling that. So for the heap, you are controlling it. Now in Java, you probably didn't see it yet, right? So in Java, the heap is working a bit differently. Heap, when we're talking about the heap, we're usually talking about C or C++. In C, C++, you manage the data yourself. In this case, there is a function called a mem_alloc, memory allocation. You're basically saying, I want to allocate that much bytes, that many bytes, please give it to me. And then it returns you a pointer. And then dalloc basically returns it back to the operating system. Anyway, so let's jump from this like high-level explanation, statically based allocation, right? Based allocation. Okay. Along with local variables, the compiler typically stores a variety of other information associated with the subroutine, including arguments and return variables, right? So information, typical source variety of other information associated with the subroutine. Okay, including arguments and return variables. Modern compilers keep these in the registers whenever possible. Compilers whenever possible. But sometimes space in the memory is needed. Okay, so when they're talking about registers, they're talking about the registers which are the closest units to the CPU, right? So you probably know that usually like each CPU has 32 registers. Those are 32 registers, usually like 4 bytes each. Yeah, 32 bits, 4 bytes each. And those are the closest to the CPU. The access time between the CPU and the registers is like approximately 1 cycle, 1 or 2 cycles. Although in order for the CPU to go to the RAM, it takes like a couple of hundreds of cycles. So it's super quick. Okay, temporaries. Okay. Temporaries. These are usually intermediate values produced in complex calculations. Okay, so imagine that you have like, I don't know, x is equal to 2 plus 5 times 3 power, like square root of that, then like to the third power, then I don't know, cosine of that, and then you multiply it by the, I don't know, tangent of 30. So that's like, obviously you can't break it all, you can't do like in one line, in one instruction, so you have to break it down into pieces, and in static, some of the intermediate values are allocated statically as well. Okay, a good compiler is trying to keep them in registers as well. Okay, so why so, right? The idea is that if you have a complex if you have complex calculation, okay, so whenever you created some intermediate results, you better store them in a place which is easily accessible, which is quickly accessible, and was the quickest ever accessible memory for the computer. That's the register. That's registers. Okay, that's 2 and 3. Bookkeeping. And that's definitely stored in the like statically, 100%. Okay, nobody's going to store bookkeeping information in the registers. Okay, so this may include subroutine return address, a reference to the stack frame of the caller. Okay. Dynamic link. That's the name, technical name for it. Dynamic link. Additional saved registers. Registers. Okay. Debugging information. And various other values. Yeah. Okay, cool. So there are obviously there's a lot of stuff. There are a lot of things which you do not see the compilers doing. So for example, say you have a stack. Okay. Let's say you have a stack, and like so that's, I don't know, that's your browser. Sorry, not the browser, but that's the operating system, that's the browser, that's the I don't know, some bookmark. And in order to shut down the computer, you need to go, it's a stack, right? So you need to go like from here top to bottom. That's why you need to, first off, you need to cross this guy out, so you need to close this one, right? And when you close this one, how does it know like where to jump back? So like how does it know what the size of this frame is? So that's usually kept and also like kept statically. Okay, the frame pointer, right? So like where's the address where the operating system starts? Okay, so what is this, right? What is this address? And this address is usually kept also statically as well. Okay, so what else want to tell you about the static allocation? Okay, yeah, supplementary routines for trans C. Okay, cool. Yeah, let's stop here. So that's statically. That's probably the most boring thing out of those three. Okay, now stack based. Stack-based allocation. Okay. Stack-based allocation. Da-da-da. Okay, so it is most useful when we do not know the amount of memory we need during the compilation of your program. Okay. Okay. So examples would be okay, so array of integers with the size defined by a variable. Okay, not sure if you remember, but in Java, for example, you can do something like this. You can say int array is equal to new int, okay, and then you can say, for example, x. Okay, but then what is x? X actually int x is equal to, I don't know, input dot next int. Okay, input dot next int, which basically means that you're scanning a number from the input, user input, and then you create an array with the size of x. Okay, so you have no idea how big x is. Okay, so like, and so that's why it can be million, can be trillion of integers. You don't really know. That's why you actually you would have to use it. You would have to use the stack, because like static space is limited. Okay. Also, if language permits recursion, static allocation of local variables is not possible. Okay, that also makes sense, I guess, because again, so like if you have recursion, in this case, you can call the same method like multiple times, like huge amount of times, right? In this case, you have no idea how to predict how many times this will be called, because it usually also depends on some kind of variable. That's why it has to be something dynamic, and static is not dynamic, because static is static. Static memory is static. That's why it's not dynamic. Okay. Yeah, so in Fortran, in the very early versions of Fortran, recursion was not an option. That's why all the local variables were located statically. Nowadays, again, since we have recursion, all the local variables have to be located dynamically. Yeah, which we're going to use a stack. Okay. Yeah. Since the number of a variable that may need to exist at the same time is unbounded. Okay? Each instance of a subroutine, by subroutine we mean method, not the main method, right? All other methods, at the runtime has its own frame on the stack. Okay, containing arguments and return values, local variables, temporaries, and bookkeeping information about that subroutine which is being called. Okay, so it's different from this subroutine. Okay, that subroutine specific about that function call. Temporaries and bookkeeping information. Right, okay. Arguments to be passed to subsequent routines lie at the top of the frame, where the callee can also easily find them. The organization of the remaining information is implementation dependent. Okay, so it varies from a language machine and compiler to another. Okay, hope it makes sense. Let me draw that. Okay, so let's imagine again that we have. Let me erase this. Well, okay, let me completely remove it. Removed it. Okay, so let's imagine that's our stack. Okay, now that'll be the first subroutine. So again, let's say that's a main function. Main function called some other function. Okay, that's some other function called some other function. Okay, and so on. So I don't know. Let's say main. Okay, method A, method B, which is being called, right, and method C. Okay. Now, if we try to kind of think about what each one of them contains, let's say method C. Okay. Well, let's say there is also like one more. Okay. So, what does each one of them contain? So there'll be 1, 2, 3, 4, 5. So that's 1, 2, 3, 4, 5. Okay. So these will be arguments to called routines. Okay. This will be all the everything, all the temporaries. Okay. Here we're going to have local variables. Okay. Then here we're going to have miscellaneous bookkeeping. Okay. And return address. Okay. Okay. Now over here we're gonna have something which is called, we'll make it blue. That's going to be frame pointer. It basically points to a position in the memory where, how do I say that? So kind of like, so the return address means that when you're done with this method, like where you going, okay, so where you living, where should you jump to, okay, where the process should jump to. So like where do I return when I'm done with this, okay, that's the return address. And the frame pointer is basically the start. So but everything else is all about that function call. So the frame pointer basically points at the location of the memory where you start the section of the memory talking about specifically that function call. Okay, so basically everything related to the function call apart from the return address, where you return after you're done. And okay, that should be S here. Okay, return address. Okay. Yeah. So that's one more thing is the stack pointer. Sorry, no. Okay, so that is called a stack pointer. Okay, so what a stack pointer does, it points to the location of the memory. If you call another method, let's say that's method C, that's method D, and you call method E, where to place information about that the new method, the method E. Okay, so that'll be placed in the address of the memory where the stack pointer is, and of course again that's going to continue. So that's not the end of the stack, right? That's that kind of infinite both ways, approximately. Okay, yeah, so that will be stack-based, stack-based allocation. A couple of more things I wanted to talk about. Which time do we have? Okay. Yes, prologue and epilogue. Okay, prologue and epilogue. Okay, maintenance. Again, so stack-based allocation. Everything which is located on the stack. Is not maintained by a person, right? By programmer. So the system maintains it. So maintenance of a stack frame cannot be predicted at compile time. The offsets of objects within a frame offsets within a frame usually can be predicted, can be determined. Okay, so offsets, what does that mean? That means okay, so for example, how do you know like how much memory do you need for this one instance of a method? Let's say again, so let's say 2 megabytes, right? And so like return address, how much does that take? Plus how much does this 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 take? Let's say it's 2 megabytes. Okay, so where do you start miscellaneous bookkeeping? Where do you finish return address? Okay, so that's the offset of the return of the bookkeeping. Okay, so where do you start local variables? So like this plus this, that's the address of the where you start local variables. This plus this plus this, where the temporaries lie, right? And this plus this plus this plus this, that will be the address of where the argument to the called routines also lie. Okay, so the compiler needs to calculate the offsets in the memory. So how much does that take? That takes, in order to know where to put the temporaries, local variables, all that stuff. Yeah, so that can be determined. Compiler can arrange for a particular register known as a frame pointer to always point to a known location within the frame of the current subroutine. Code that needs to access a local variable within the current frame or an argument near the top of the frame can do it by adding a predetermined offset to the value in the frame pointer. Okay. Access thing. Okay, the idea is this. If let's say again you have a frame pointer and you need to access some local variable, right? So basically what you need to do, you need to add the offset of like the offset of this section, okay, which I guess would be equal to the size of the miscellaneous bookkeeping to the frame pointer, and that's how you get to over here to the that's how you get the address of the local variables. Okay, now about the prologue and epilogue. Okay. Okay, yeah. Prologue, epilogue. Okay, so maintenance. Last thing. Maintenance of the stack is the responsibility of the subroutine colon sequence. The code executed by the caller immediately before and after the call. Okay, so that's all something which is kept in static memory. Before and after the call. No, hold on, sorry. That's different. So subroutine colon sequence. Okay, the colon sequence, and of the prologue, which is code executed at the beginning, and epilogue. Code executed at the beginning, and epilogue code executed at the end of the subroutine. Okay, yeah, so that's what I want to say. So maintenance of the stack is the responsibility of the subroutine colon sequence. That's a technical term. Okay, the code executed by the call immediately before and after the call, and the prologue, the code executed at the beginning of the subroutine, and the epilogue, the code executed at the very end of the subroutine. So the kind of those three things: the prologue, epilogue, and the colon subroutine. Colon sequence. Subroutine colon sequence. Yeah. Okay. Yeah. Hope you guys enjoyed this class. That's for now. That's it for now. That's it for the stack-based allocation. Okay, so we'll talk about statically stack-based allocation. Now, next time we'll be talking about the heap-based allocation, which is also a lot of fun. It's also complicated how it's all done. So we'll dive deep into the memory management of the computer. I'll see you guys later. Bye.